We have a plank, lots of information given, but it's all given on the diagram. And then we're told so actually I'm just going to apply the other forces. So there's going to be a weight acting down, and because it's a uniform plank, it's going to be precisely in the middle. I don't know exactly, it's not necessarily going to be in the middle of the zero point 0.5 here, so I'll just put it slightly off center. But this length is going to be 2 meters because it's uniform. It's the weight acts in the middle. Then I've got a reaction force from C, and in fact, I'm told what that is, so it's just going to be 75. And then a reaction force from D, which I don't know what that is, so I'll call that RD. So I forgot to put 100 on. Now, we're asked for the reaction force at D. What we can do is resolve forces in the vertical direction. So 75 plus RD is going to equal 100, and therefore RD is going to be 25 newtons. You could, maybe just go straight and write that down. Fine, I've just sort of shown where it comes from. Brilliant. Right, there are all our forces. Now we're asked to work out the value of x because we're told that the plank is resting horizontally. There's going to be no moments, and therefore I can take moments. So I'm going to take moments about you could take moments about C or D or the weight to avoid that, but we want to find out what X is. So the simplest thing is just going to be to take moments about A, because then we won't have to mess about with X then, which you would if you start taking moments about a different point. When we take the moment involving the force of 75, we're just going to get an X in there. So first of all, clockwise moments. It's going to be 100 acting down and then times by, so force times distance, 100 times 2. Remember, it's the perpendicular component of the force, but they're all perpendicular here, so we don't need to do anything with the angles. It's just 100 times 2. And that is going to equal the anti-clockwise moments. So remember, this is a pivot, and the 100 is sort of trying to make it move this way. That's why it's a clockwise moment, whereas the other two are trying to make it turn this way. Okay, like so. That's why I'm calling them anti-clockwise moments. So it's going to equal 75 times x plus 25 times x plus 0.5. Could also, um, take I've taken moments, but I'm sort of resolving. Basically, I'm saying the clockwise equals the anti-clockwise. You could also just add them together and set it equal to 0, but ultimately you're going to end up with this equation as well. That means 200 is going to equal 75x plus 25x. So 200 is actually 100x plus 25 times 0.5, which is 12.5. And that means what we're going to get, we're going to do 200 minus 12.5. So 100x is going to be 187.5. And therefore x is equal to 1.875 meters. Nice. Right, in the next part, we've got a new setup. So I'm going to draw another diagram. I could try and start crossing out numbers on the original one, but I just think it's good it doesn't, to just draw a fresh one. So again, we've got this weight acting down with 100. And then we're told that a stone is being placed at the end at B. We don't know its weight, so I'll just call that W. And something important here is that it says it's about to tilt about D. Now, what that means is it's going to end up, well, presumably the stone is going to be heavy, and it's going to make it sort of go, it's going to tilt like this ultimately. Now, because it's about to tilt, it's not quite moving, but it's about to move. And the upshot is that there is no normal reaction force at C. That's what you have to realize. So I'll just write RC equals 0. I'm not going to put it on my diagram, which leaves me with RD. Right. We could use F equals MA to equate those, but I don't think we need to. We're trying to work out what W is, and I can just avoid RD if I then take moments about D. Now, actually, I've just remembered I've got a couple of other things to add. We know that this is 1.875. It's still going to be the same from part A. And then because that is 0 0.5, I can work out this distance. I haven't done that yet. So 1.875 plus 0 0.5, and then 4 minus that is going to give 1.625. So of course, you can work out RD, you can take moments wherever you like, but it's going to make sense to take moments at D. So W is going to be like, so this is my pivot point now. W is going to be trying to move it clockwise. So it's going to be 1.625 times W. And then the 100 is the thing that's trying to make it go the other way. And that's going to equal 100. Now I haven't worked out that distance yet. So for this one, it's not going to be 0.5. Remember, it's in between. I'm going to need to, I probably should have done this before, apologies. But it's going to be halfway, so it's going to be 0.375. And so by taking that moments about that point, we've got a formula just for W. So 100 times 0.375 divided by my answer, which was the 1.625, gives me 23.076. A little bit surprising that we've got something that, is a decimal, but that is the answer. So I'm going to round it to 23.1 newtons. So we worked out the weights. We just have to explain the limitations now of modeling the stone block as a particle. So particle means it has basically 0 dimensions. It's just like a single point in space with some certain properties. So some things that it neglects is, say, air resistance because it doesn't have a dimension. That's not valid here because we're dealing with a situation where something is just sat there. But you need to think what would happen if it wasn't a particle, if it was like a block like this. And now the weights would definitely not act exactly at B. It'd be a little way along. And so basically what we've done here is assumed. So it assumes center of mass is at B. In reality, it will be slightly to the left. Depends how big it is as to how far as well. And then what about modeling the plank as a rigid rod? Well, if it's rigid, that just means it doesn't bend, and that is the limitation. So in reality, the rod may bend. Depends what it's made of, depends how heavy the weights are. So I'm happy with those answers. Just going to show you what the mark scheme says. They expand on it slightly. Modeling the stone as a particle assumes the weight of the stone acts exactly at B, and therefore the block's dimensions have not been taken into consideration. I didn't sort of say that, but I kind of said what would actually happen if we did take the dimensions into consideration. Modeling the plank as a rigid rod assumes that the plank remains in a straight line and does not bend. So I didn't say the straight line bit, but that's kind of implied. All right, nice question on moments. Well done.